So we continue. So now we know what is FM, PM, modulation index and their sidebands. So now we want to know how to calculate their bandwidths. So the higher the modulation index in FM, the greater the number of significant sidebands and the wider the bandwidth of the signal. As if you noticed in the Bessel function table, when the modulation index increasing, you had too many number of sidebands with significant amplitude or power. So that is meaning this. So when a spectrum conservation is necessary, the bandwidth of FM signal can be restricted by putting an upper limit on the modulation index. So we can limit that modulation index to a smaller value like a narrowband FM. Okay, so let's see how we can calculate the FM bandwidth. I am showing you how you calculate through an example. If the highest modulating frequency is 3 kilohertz and the maximum deviation is 6 kilohertz, what is the modulation index? Of course, we can calculate, we know this. So FD over FM, so we have 2 as our modulation index. So now, since we know our modulation index, what is the bandwidth? So the bandwidth equation is this: 2 times FM times N. FM is the maximum frequency of the modulating signal. N is the number of significant sidebands, which we need to refer to the Bessel table or Bessel function. So we need to check how many sidebands are significant. Significant means more than 1% compared to the carrier power. So then we can include here, then we know the bandwidth. So for this example, the modulation index is 2. So then from the table, we see there are 4 sidebands. 1, 2, 3, 4. So N is equal to 4 then, and then we just follow the equation. FM was 3 kilohertz, maximum frequency, times 4 sidebands. You just write the value 4. You don't need to take care of what are the sidebands amplitude. As long as all of them are larger than 1%, if you use the table, of course, is only written those. The smaller is not available. But if you refer to graph, Bessel function graph, so then you need to only take care of those which are bigger than 0.01. So then we have 2 times 3 times 4, we have 24 kilohertz. This is the bandwidth of our FM signal. If this was AM and the maximum frequency of the modulating signal was 3 kilohertz, we only needed 6 kilohertz. So bandwidth, but here we need 24. So other than this method just now we see, Another way to determine the bandwidth of an FM signal is to use Carson's rule. So what Carson's rule is telling us, this rule recognizes only the power in the most significant sidebands with amplitudes greater than 2% of the carrier, or 0.02 or higher. This is the equation, means it's 2 times the maximum frequency deviation plus FM, maximum frequency of your signal. So you combine these two frequency times 2. Sometimes you may not find this easily or directly follow the 2% because this doesn't relate it to Bessel function at all. It doesn't need any information from the table. It's just based on the maximum frequency deviation and the maximum frequency of your message signal to determine what is your bandwidth. But this approximately is around this range of 2%. Means consider more significant elements in the spectrum. If we use our previous example, the last example, according to Carson's rule, the bandwidth of the FM in our previous example is 2 times 6 kilohertz, which is frequency maximum deviation, 6 plus 3 kilohertz, which is maximum modulating frequency. So then we have 6 plus 3 become 9 times 2, 18 kilohertz. So 18 kilohertz, of course, is less than 24 kilohertz. So here, if you put 3 here, let's say we only took 3 sidebands, then n was 3 times 3 become 9 times 2 become 18, become similar to this. So means based on Carson calculation, only 3 of your sidebands are available in the receiver side. The rest will be eliminated and filtered out. So means you won't get the 4th sideband, and you will have a little bit less power, of course, in this case. But that is, as we said last time, there is a trade-off between the power and bandwidth. Here is something explaining about this. Carson's rule will always give a bandwidth lower than that calculated with the formula bandwidth equal to 2 FM times N. This is always is the same, means always Carson bandwidth is smaller than the one we use the Bessel function or this equation. However, it has been proved that if a circuit or system has the bandwidth calculated by Carson's rule, the sidebands will indeed be passed well enough to ensure full intelligibility of the signal. Means it's just sufficient to fully recover your signal, and there is enough power as well to get your signal. That means it's not just some equation or a method. It has proven that is good enough to be used as well. Let's have one example. what is the maximum bandwidth of an FM signal with a deviation of 30 kilohertz and a maximum modulating signal of 5 kilohertz as determined by Bessel function-based equation, which is figure 5.8, and second, Carson's rule. So our first method is use the modulation index. We calculate modulation index, so maximum frequency deviation 30 kilohertz divided by maximum modulating signal frequency 5 kilohertz. We have modulation index of 6. Then we take this value, go to our Bessel function table. So here in this table, from the first column, we search for modulation index of 6. Then we find how many sidebands, significant sidebands we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, which of course you can see from here as well. There are 9 sidebands for modulation index of 6. So then in our equation, we have 2 times maximum frequency of the modulating signal, which is 5, times 9 sidebands. So then we have 90 kilohertz bandwidth we need for this message or this signal. So this is using our initial equation, considering the sidebands calculated from using Bessel function. Second method, we use Carson's rule, so which not relate to the Bessel function table. So we just use the maximum deviation of the carrier frequency plus maximum frequency of your message signal, which is 30 plus 5 kilohertz, become 35, times 2 is 70 kilohertz. So you can see one becomes 70 kilohertz, another one is 90 kilohertz. So that is how we can calculate the bandwidth of our FM signals.